Hi, everybody. If you're watching this, you survived the almost hour-long double lesson, or maybe you took a break in the middle like I suggested. Either way, this is your last lesson for probability in terms of new content. And this is working with probabilities. And our learning goals are to explore the context of probability, realize probabilities are collected from real life events, and then we're going to use probability to help predict future events. Today's lesson's a lot more of the practicality of probability, and even a little bit how stats and probability go hand in hand. So maybe you're asking yourself, maybe why do you care about probability? So probability and stats are constantly presented through the media in a variety of contexts. Stats are collected from real-life events and/or studies, and stats, like probability, help predict results of future events. So that little picture does a good job of explaining kind of what we did last unit versus this unit. So last unit, statistics, given the information in your hand, what's in the pail? So you've taken a sample size, you want to know what's in the pail. Just like when we do a survey, if you've ever been asked to fill out a survey, even anything that you do on social media, Instagram, Twitter, when you buy something and you get a receipt, they have surveys. Not every single person in the world is filling out that survey, right? So they take a look, who's done it, collect some demographic information, collect thoughts and opinions based on everyone who filled out the survey. Can you make some generalizations about the population? Whereas probability, this unit, given what's in the pail, if you randomly draw something out or randomly grab a handful of marbles, what's likely to be in your hand? So it's the opposite. Examples in the media in real life. American Idol, a lot of other shows where they have people call in for their vote or text in a vote or go online for a vote. That's all probability and statistics. The Weather Network. If you've ever looked at the weather app on your phone, whenever you see POP, that stands for probability of precipitation, meaning based off of what they know is coming weather-wise, what's the likelihood that there's going to be snow or rain or ice or any other form of precipitation. Anytime there's an election, they always make predictions. They take surveys, they take polls. They try to make predictions on the election results. Sports gambling. Again, nothing in life is guaranteed. Anytime you gamble, casino, sports, there's always odds calculated, and there's always a favorite and an underdog, and you can place wagers. And we're actually going to talk a little bit about sports gambling for this lesson. Continuing with sports, draft lottery, they put a weighted number of entries, they draw, and that's how they come up with a draft lottery for NHL and NBA. And then in the middle there, those are all insurance companies. Insurance is basically based off of probabilities. So if we talk about house insurance, where do you live? What's the value of your house? What's it made out of? How old is it? Things of that nature all affect your insurance. For you guys, the insurance that you would care about most is probably car insurance. Now, if you ever wondered how they come up with your premium, it's based off of probability. So for instance, Males tend to pay more than females because, statistically speaking, they are more probable to get into accidents. If you drive a certain color of car, for instance, red, for some reason, red statistically is more probable to get into an accident, you pay more. If you are under a certain age, so if you are under 20, again, statistically, they say, well, people under 20, or maybe it's under 25, they speed more likely to drive dangerously, higher insurance. If your vehicle is 2 doors, that's considered a sports car, even if it's not. Sports cars drive faster, statistically speaking, get into more accidents, statistically speaking. Therefore, you are more probable to have to get into an accident and have to make a claim. So those are just some very quick examples of, maybe you haven't realized it, but it involves probability and statistics. So for the rest of this lesson, we are going to do some examples. MNR stands for Ministry of Natural Resources. So an MNR employee caught and tagged 50 fish in a lake. If 30 were pickerel, 5 were bass, 15 were pike, find the experimental probability of getting A, B, C, and D, all as a percent. Don't forget, for good communication marks, capital P for probability, and then in brackets what you want the probability of. Now it says that they caught and tagged 50 fish. So we know it's out of 50. How many were pickerel? Well, it tells you there's 30. So 30 out of 50. That's the experimental probability, because that's just what they caught and tagged. 30 divided by 50 times 100, 60%. Probability of a bass. How many bass were caught? 5 out of 50. Converted to a percent, 10%. Probability of a pike. 15 were pike out of 50 fish that were caught and tagged. 15 out of 50 is 30%. As a quick self-check, those were the only 3 things that were caught, so that makes up all 50 fish. And if that makes up everything, you know that should add up to 100. Which, if you double check that, 60 plus 10 plus 30 is 100. D, probability of not getting a pike. So you could count up everything that's not a pike, or you could kind of think about it in reverse. I know, so I'll change my color here. I know the probability of getting a pike was 30%. So probability of getting a pike is 30%. The probability of not getting a pike would be what's left over, which we know 100% is the maximum. So if 30% are pike, that means 70% aren't pike. If you don't get that logic of thinking, just count up what's not pike. So what's not pike would be the pickerel and the bass, 35 out of 50. And if you do some very quick math, 35 divided by 50 times 100, 70%. Just another way to think about it. Same question, except for we got 3 more. So you don't have to recopy down the initial information. And I see there's a typo here. EF, that should say G. So we still want to know the probability, still in percents, of catching a bass, releasing it, then catching a pike. We can kind of cheat again, probability of all that. So there's actually two things that are happening here. So what's the probability that you pick out a bass? 5 out of 50. It says you release this, you put it back. Then catching a pike. How many are pike? 15. And since you put the bass back, there were still 50 fish. Whenever you have a question like this where there's two or more things, you multiply. So if we do 5 divided by 50 times 15 divided by 50 times 100, because we want a percent, we get 3%. So that's pretty low, pretty unlikely. Catch a bass, put it back, then catch a pike. So getting both those things simultaneously. F, probability of catching a bass, keeping it, then catching a pike. So this question looks almost identical except for these two words, releasing, keeping. It's kind of like that question we did in a previous lesson, if you remember, about the Queen of Hearts. So I asked, what's the probability of drawing the Queen of Hearts? What's the probability if you don't draw it the first time, but then get it the second time? Or try to draw it the second time and you don't put the card back. So probability of catching a bass is still going to be, how many bass do we have? 5 out of 50. Since there's two events happening, we're going to multiply. But this time you keep it. So instead of there being 50 fish, if you've kept one and you kept the bass, there's no longer 50 to pick from. There's only 49. And how many were pike? 15. Use your calculator. 5 divided by 50 times 15 divided by 49 times 100. And let's just go to two decimal places. 3.06%. So you have a slightly better chance of having both those things happen. And that makes sense, because if you caught something that was not a pike and didn't put it back, you have less options to pick from. One less, in fact. And that's what's contributing to that, 6/100ths of a better percent. G. If there were known to be 3,500 fish in the entire pond, how many would you expect of each? So we haven't caught all 3,500. We only caught 50. So this is kind of like, based on the information that's in our hand, what's in the lake? Or sorry, pond in this case. These are not probabilities. It's asking for how many, so we're not going to use P for probability. And we're actually going to go all the way back, or you're going to refer back to the previous slide. So let's start with pickerel. Pickerel we calculated to be, if you look back at A, 60%. Now you can't work with percents. You have to convert them back to decimals. And if you've forgotten how to do that, 60%, so maybe I'll do that just for the first one. 60% divided by 100%, which is 0.6. And we want to know what 60% of 3,500 is. In other words, 0.6 times 3,500. And if we do that, 3,500 times 0.6, we get 2,100. So we would expect 2,100 pickerel. May not be the case, but that's what we would expect based off the information that we have. Same idea for the bass. I'm not going to show all the steps this time. If we refer to part B, 10% were bass, that's 0.1. We know 10% of 3,500 should be how many bass there are. That's 350. And then last, pike. Based off the last slide, part C, 30%, so 0.3 times 3,500. And we should get 3,500 times 0.3, 1,050. And if this was a test question, how could you check your answer? Add up all those numbers. 2,100 plus 350 plus 1050. Lo and behold, 3,500. If we didn't get 3,500, we know we made a mistake because those are the only 3 fish that we caught and tagged in the lake. So they have to add up to 3,500. Our next example, we're going back to getting information from a graphic. So students were surveyed about 2 sports, basketball and football. How many students were surveyed? I've given you the numbers on top of each bar, so all you have to do is add. So I'll just write here a little note, add all the bars. When you do that, you should get 1195. What is the probability that a student likes basketball but not football? So we'll cheat a little bit. Probability of all that equals. Now we know we surveyed 1195 students. What's the probability they like basketball but not football? That would be just this bar. So 190 out of 1,195. Again, since I didn't tell you to leave it as a fraction, decimal, or a percent, you can leave it however you want. However, that fraction probably means very little to anyone. So usually, if that's the case, to make sense of it, we'll convert it to a percent. Top divided by bottom times 100, 1 decimal place, 15.8%. What is the probability they like either, but not both? Probability of all that. So they like either, but not both. So that means we're not including that one, and we're not including that one. So we want to know this one and this one. And since it says either, we're going to add, whereas for the Ministry of Natural Resource question, it said this, then this, or this and this. That's why we multiply. But if it's either, we're going to add. So the probability they like basketball, 190 over 1195, plus the probability they like football, which is 340 over 1195. When you add those up, 106 over 239, and that's the reduced fraction. Again, that means nothing probably to most of you. Convert that to a percent, 44%, less than half. Makes a bit, that number, that changing it to a percent makes it a little bit more livable for us. Or relatable, I should say. What is the probability that like basketball, football, or both? So basically we are going to include, so basketball, football, or both, but we're not including this one. Since this isn't like and it's like they like this, or this, or this, it's like our either, we are going to add. So probability of all that. So 190 over 1195 for basketball, football, 340 over 1195, plus the ones that like both, 565 over 1195. Add those all up. And you should get 219 over 239. And if we make that a percent, just have a bit more meaning, 91.6%. So basically a very high percentage, which that makes sense because those are the three highest bars. We added them up. The neither bar, that was the smallest bar of all of them. So that's getting information from a graphic. So now we are going to move on to a betting question. And you might want to make sure you know how to do something like this. So Jimmy Howard of the Detroit Red Wings, this is an older question from a previous season. Jimmy Howard of the Red Wings has an .882 save percentage so far. The Leafs are averaging 33 shots per game. How many goals would Toronto expect to score? So again, nothing's guaranteed. This is just expected. And this is how, when they talk about things like the Vegas odds or sportsbook odds, that's how they come up with like these over-under numbers, who's the favorite, what's the spread, stuff like that. This is not a probability for part A, so we're not going to use the P. How many goals would Toronto expect to score? Well, we know the Leafs take 33 shots. We know Jimmy Howard saves 0.882 of those. So if we do 33 times 0.882, we'll go to one decimal place, 29.1. Now that's how many saves. So we talk about save percentage, that's how many saves. So that's how many shots Jimmy Howard would expect to save. Well, whatever's not a save is obviously a goal, and we're being asked for goals. So if we want to figure out how many goals the Leafs would expect to score, we would expect them to score. They take 33 shots. Jimmy Howard, based off probability, we just calculated, would save 29.1 of them, which means 3.9 goals. Obviously, you can't score 0.9 of a goal, but when it comes to odds, it's usually to decimal places. Would you bet on Toronto to score less than 2 goals or more than 2 goals? Based off of what I just saw, I would bet, they're expected to score 3.9, so I would say bet to score more than 2. And the Y would be right there. They're expected to score 3.9, or almost 4. Currently on some sportsbook, it pays 2.01 for Toronto to score 2 goals or less. How much could you win on a $50 bet? So generally speaking, whenever you make a bet, it's your money, your bet, times the odds. And that's the odds. So that means we're going to bet $50 multiplied by 2.01 equals 150. And that makes sense. The higher that odds number is, so the higher it is, the more unlikely an event is to happen, which makes sense. We just calculated that the Leafs are expected to score almost 4 times. for them to score 2 or less, that would be unlucky. So maybe Jimmy Howard plays over his head, plays crazy, or the Leafs can't finish. Something like that. Who knows? Again, that's why they say play the games. So you kind of went contrarian on your bet. You bet for something unlikely to happen, and you ended up more than doubling your money. You started with 50, you walked away with 150 cents. You won $50.50. Are you guaranteed to win or lose? I basically just talked about that, and I've talked about it in previous examples. No, nothing in life is guaranteed. That's why they play the games. Sticking with sports, fantasy football. So, and you don't have to know anything about fantasy football or fantasy sports. I will always give you information like this, and then you just have to kind of piece it all together. So in fantasy football, running backs get 6 points for a touchdown, 1 point for every 10 yards rushing or receiving, and half a point for every reception. Alvin Kamara of the Saints, New Orleans Saints, for those that follow football, through 5 games, has 281 yards rushing, 7 touchdowns, 395 yards receiving, and 38 receptions. How many fantasy points does he have on the year? So, again, you don't have to know anything about fantasy football. I've given you all the information. So let's start with the first thing. You get 6 points for a touchdown. He's got 7 touchdowns. So just to organize what we're doing here, touchdowns, he has 7 of them. You get 6 points per touchdown. That's 42 points. The next thing, you get 1 point for every 10 yards rushing. He has 281 yards rushing. So he has 281 yards, but you only get a point for every 10. So you got to divide that by 10. And that equals 28.1 points. Receiving. Again, same point allocation. 1 point for every 10 yards receiving. He has 395 yards. You get 1 point for every 10, 39.5. And then the last thing, receptions, which just means catches. He has 38, so 38 receptions, and you get a half a point for every reception, so times 0.5. 19 points. So when we want to know how many he has on the year, add all those up. So his points on the year, add all those up. Hopefully you get 128.6 points. Sticking with that same question details, so you don't have to recopy the details. How many points is he averaging per game? And again, these aren't probabilities, so we're not using the capital P. Well, he just got 100. We just calculated 128.6. So far, he had played 5 games. Divide that by 5. He's averaging 25.7 points per game. How many points would you expect for this season if it's 16 games? There's a couple ways to do this, but the easiest way, in my opinion, once we've calculated his points per game, this is how many he's getting per game. and the season's 16 games, multiply that by 16. And you should get 411.2 points. Is this guaranteed? Again, the answer is no. Nothing in life is guaranteed. Except for things like, could you roll a 7 on a 6-sided die? Stuff like that. So no, nothing is guaranteed. Obviously, a player could get injured. He could have a tougher part of the schedule. If we look at this past year, he maybe got placed on the COVID list and couldn't play a game or two due to COVID. So he's not guaranteed to get those points.